Hello, everyone. My name is Hoàng Ngo. I'm working in Chalmers University of Technology in Sweden, and I'm going to present a work on the achievable rate regions for the two-user MIMO broadcast channel with transmit correlation diversity. And it is a joy to work with Zhang from Centre Supélec, Paris-Saclay University, France, and with Fan Zhang and Arya Nosratinia from University of Texas at Dallas, USA. So let me start. Well, in MIMO wireless communications, the channel state information is important because it can enable to adapt the transmission and reception to the current fading state. However, there is no free lunch because this information is not given for free. It has to be estimated, typically using bylaws and feedback, but bylaws occupy some communication resources. And also there is the channel estimation error, and in some situations, orthogonal bylaw assignment can be infeasible. So it would be more general and more practical to assume that the channel state information is unknown a priori. And in this case, we have non-coherent communication. Well, in our work, we consider the non-coherent MIMO broadcast channel with a transmitter with M antennas and two receivers with N1 antennas and N2 antennas. And the channel between them is assumed to be block fading with coherence time t. This means that the channel is constant for each coherence block of length t symbols, and then it varies independently between the blocks. Now, within each coherence block, the transmitter sends a signal X, which is subject to the power constraint P, and the received signal at each receiver or each user has this form. So it is the product of the transmitted signal X and the channel matrix H added with a noise which is Gaussian. We assume that the channel is spatially correlated according to the Kronecker model. So the channel matrix can be written as the product of the two terms. The first term is a random fading matrix, a GK, which is assumed to be unknown. And the second term is a correlation matrix. Here we use lambda sigma k to denote the diagonal matrix containing the eigenvalues of the correlation matrix. And we use U to denote the matrix containing the eigenvectors of the correlation. We assume that the correlation matrix for user K is of rank Rk, and this matrix is deterministic and unknown. We also assume that we have a transmit correlation diversity, so the correlation matrices for different users are different. In other words, the two users experience different correlations structure. So now we can get a bit more in deep in the correlation structure. Here we use Vk to denote the column span of the matrix Qk, and we call this subspace the correlation eigenspace of the user K. Well, if the eigenspaces of the two users are not overlapping, then we can use a joint spatial division multiplexing scheme to reduce the training overhead. However, in practice, the subspaces can be overlapping, as in the example that we show here. So here, the subspaces V1 and V2 are overlapping, and we call the overlap or the intersection between them the V0. We assume that V0 has dimension R0, which is, of course, smaller than R1 and R2. And we also assume, without loss of generality, that R2 is smaller than R1. Now, for this channel, some achievable degree of freedom or rate pre-lock regions have been characterized in our previous works. However, the rate regions is still open. So in this work, we would like to derive some achievable rate regions for this channel. Well, first of all, we consider a baseline scheme, which is based on orthogonal transmission or TDMA. So in this scheme, we activate only one user at a time and let this user achieve a high rate while the other user achieves 0 rate. in order to compute the rate for the active user, we need to extend the analysis of Hassibi and Hochwald in 2003 to the case of correlated fading. So this is analysis of the rate for a pilot-based scheme in which the transmitter sends some pilot followed by Gaussian data. The receiver estimates the channel using the pilot and an MMFC channel estimator. And the key argument here is that the worst case uncorrelated Gaussian noise has Gaussian distributions, so that we can replace the effective noise after channel estimation, after the equalizer, by a new Gaussian noise. And with that, we can derive the rate. Now, the new thing is that we can let the transmitter, in our case, to exploit the correlation matrix to transmit only in the effective channel directions instead of transmitting in the full space. So let's consider an example with coherence time 24 and 16 transmit antennas, 12 receive antennas at each user, and the SNR is 30 dB. We assume that the rank of the channel of the user 1 is 10, of the user 2 is 6, and the rank of the intersection is 4. So here we plot the achievable rate regions. We plot the rate of the user 2 versus the rate of the user 1. And the achievable rate regions with TDMA is a triangle. If we transmit in the full space, the region is quite small because we have to dedicate some channel uses to learn even the ineffective channel directions. Now, if we exploit the correlation, we transmit in the effective channel directions only, then we can improve the region. So that's a baseline. In the following, we are going to show our achievable schemes, and let's see how much we can improve upon this. So the key component of our proposed schemes is precoders. So based on the correlation matrices, we can build some precoders. The precoder V0 with the column span inside the intersection of the two channel subspaces. We also build the private precoders V1 for the user 1, and the column span of V1 is inside the private subspace of the user 1. And similar for the precoder V2 of the user 2. Here, the parameters S0, S1, and S2 are the ranks of these precoders, and we can play with this parameter. We can choose as S0 from 0 to R0, S1 from 0 to R1 minus R0, and S2 from 0 to R2 minus R0. Well, with that, the proposed schemes are based on pilots and some kinds of superpositions. The first superposition is rate splitting or additive superposition, in which we transmit some signals in each section, the common section and the private sections of the signal space. The second scheme is product superpositions proposed by Lee and Nosratinia, in which the signals for the two users are multiplied and then they are precoded to be in the subspace of one user. And finally, we can use a hybrid scheme, a combination of the two schemes in which we have a component which is similar to product superpositions, but we also add another term, which is the precoded signal for one user. So these are some the main points of our schemes. So now let's go into each scheme and see how much we gain with these schemes. So the first scheme, rate splitting. In this case, as I mentioned, the transmitted signal is the sum of the precoded signals in different common and private subspaces of the channels. And thanks to the precoders, user 1 sees only X0 and X1, user 2 sees only X0 and X2. So the received signal at each user is equivalent to the received signal of a multiple offset channel or the MAC with two incoming signals. So here the received signal at user K is written in this form, where the blue terms are the equivalent channels. Now, according to the red regions of the multiple access channel, we know that a pair of rates R0 and R1P is achievable for the Mark 1 if they satisfy this condition, and similar for the user 2. Now, if we have a rate triple R0, R1P, and R2P that satisfy all these conditions, then this rate triple is achievable for the broadcast channel. Here, R0 is a common rate, so we can split it into two parts. The common rates R01 for user 1 and R02 for user 2. And finally, the individual rate for user 1 is the sum of the private rate and the common rate, and the same for user 2. Now we use the Fourier Moskine elimination to obtain a set of conditions for these individual rates R1 and R2 to be achievable for the broadcast channel. And from this, to derive the achievable rate regions, we need to pick an input distribution and then compute these mutual formation terms. And we choose the input distribution as follows. We let the signals x0, x1, x2 to contain some bylaws and followed by some Gaussian data. And we arrange the bylaws such that the users can learn the common signal first and then learn the private channel at the same time. And then they can decode the data. So with this, we can compute the mutual information terms similar as in the TDMA case. And we obtain a region. So let's see how much we gain. Let's consider the same example. So here the red regions achieved with red splitting is depicted in red. It is significantly larger than the TDMA region. Now we move on to the second scheme, which is product superposition. So in this scheme, the transmitted signal is the product of the two signals for user 1 and user 2, and we record them to be in the subspace of the user 2. And in each signal, we also have some bylaws and some Gaussian data. Now user 1 communicates within the bylot phase of the user 2 only. In this phase, the received signal of the user 1 can be written in this form, where the blue term is the equivalent channel. So user 1 first estimates this channel and then decode the data in S1. And it can achieve the rate, which is the mutual formation between this received signal in this phase and S1. Now for user 2, we see that X1 is multiplied with X2, so it becomes a part of the equivalent channel for the user 2. User 2 first estimate this equivalent channel and then decode the data in S2 and achieve the rate, which is the mutual formation between Y2 and S2. So here we present this scheme in this order of the two users, but we can also switch the order and we achieve another rate pair. So we consider again the example, and we plot the rate regions achieved with product superposition by the magenta curve here. We see that we can have some gain with respect to rate splitting in these regions, where one of the two users achieve a high rate and the other user can still achieve a non-negligible rate. Now we consider the final scheme, which is hybrid superpositions. We combine product superpositions and additive superposition. So the first term is similar to the transmitted signal with product superpositions. The second term in the transmitted signal is the precoded signal as in the rate splitting. Now for user 1. Now the signal X2 prime is a part of the equivalent channel for the user 1. User 1 estimates this equivalent channel and then decode the data in S1, and it achieves the rate, which is a mutual formation between Y1 and S1. For user 2, on top of the data that is embedded in the bylot of the user 1, it can also decode some data in inside X2, which is in the private subspace of the user 2. And to do that, the user 2 has to estimate the private channel with some added bylaws inside H2 prime. So this is the main difference with product superposition. The received signal of the user 2 is of this form, where A is a matrix that contains no new information. User 2 first estimate the equivalent channel and then decode the signals in S2 prime and S2, and it achieves the rate, which is a mutual formation between the received signal and the two data matrices, S2 prime and S2. So here we note that hybrid superposition, although it has a form as a combination of the two previous schemes, it is actually not a generalization of rate splitting and product superposition, in the sense that we cannot recover exactly rate splitting and superpositions from this hybrid scheme. Now let's go back to the example. Here we plot the rate regions of product superposition in light blue. We see that we achieve some new points which are outside of the regions of rate splitting and product superposition. And finally, with time sharing, we achieve this overall region, which is the convex whole of all the regions that we have mentioned. And we see that it is significantly larger than the TDMA region. Now let's consider another example. Let's increase R0 from 4 to 5. We see that in this case, we achieve a smaller region, but the contribution of product superpositions is more significant. Or in general, we see that the rate achieved with product superposition is higher if the difference between the ranks of the two channels is larger. Now the final example. Now we let R1 to be 9, R2 is 7, and R0 is 2. So the intersection between the two subspaces is quite small. And in this case, the achievable rate is much larger than the previous case. It is getting closer to the rectangle. We see that product superpositions achieve the rate which is inside the regions of rate splitting, and the rate regions is improved a bit with hybrid superposition. So let me conclude the talk. So in this work, we consider the two-user non-coherent MIMO broadcast channel with transmit correlation diversity. So the two users experience different correlation. We have derived some achievable rate regions based on pilot and some superposition techniques, which are rate splitting or additive superpositions and product superpositions and a combination of them. So we see that with these transmission techniques, we can improve significantly the rate regions with respect to orthogonal transmission. Thank you for your attention, and we are looking forward to your questions.